Welcome to Summarize Science, where we break down complex research into everyday terms. Today we are looking at a paper titled, The Uncertain Policy Price of Scaling Direct Air Capture. You might have heard of direct air capture, which is basically a giant set of fans designed to suck carbon dioxide right out of the atmosphere. While it sounds like a perfect solution for climate change, the researchers found that its future is incredibly speculative. Currently, this technology removes almost no carbon compared to what we emit, but many plans for the future rely on it heavily. The researchers wanted to know what it would take to scale this tech from its infancy to a gigaton level, which is 1 billion tons per year. To do this, they used a sophisticated computer model to run thousands of different simulations. They looked at 36 different variables, including technology costs, energy needs, and government subsidies. One of the most interesting findings is that scaling up this technology is a fat-tailed event. This means that in most scenarios, the technology only sees modest growth. However, there is a small 4% to 6% chance that it could actually reach that massive gigaton scale by the middle of the century. Achieving that success isn't just about better engineering, it's mostly about aggressive policy. The researchers identified 3 main drivers for success: how fast the industry can grow, the amount of subsidies, and when those subsidies start. They found that for the tech to take off, subsidies would need to be at least $200 to $330 for every ton of CO2 captured. If we want to hit the big targets, the total public support could cost between $900 and $3,000 billion. That is a massive amount of money, roughly the same as the total current support for all renewable power. Interestingly, the tech's success depends on what else we are doing for the climate. In a scenario with only basic policy commitments, direct air capture remains expensive and rare. But in an ambitious, long-term strategy scenario, it becomes a vital tool that helps reach net zero goals. The paper points out that the biggest barriers aren't actually the technical specs of the machines. Instead, the bottlenecks are market penetration barriers, like how fast we can build the infrastructure and how ready markets are to absorb the technology. From an economic standpoint, the study shows that this technology requires huge upfront costs, with long wait times for a return. In the short term, deploying this tech actually looks like a loss for the global economy. But by the year 2050, it could start providing significant economic benefits, particularly if it helps us avoid the worst costs of climate change. So, what does this all mean for our future? It means that direct air capture is not a get-out-of-jail-free card that allows us to keep burning fossil fuels. It only makes economic sense if it is paired with very strong policies to reduce emissions in the first place. Without those policies, the researchers suggest the technology might just be an expensive niche industry. Essentially, the policy price of clean air is a commitment to both funding the tech and fixing our energy systems. The future of the climate may depend on whether governments are willing to sustain these trillion-dollar investments for decades. Thank you for watching Summarize Science, and stay tuned for more deep dives into the papers shaping our world.